Hello, we're continuing with section 2.3, the rational zeros theorem. Our objectives are A, the number of zeros of a given polynomial function, the rational zeros theorem, Descartes' rule of signs, and Boundless theorem. To begin, the numbers of zeros of a polynomial function. Let's recall the two main topics of this chapter thus far. In 2.1, we found the zeros of polynomial that were already factored or could be factored using techniques from earlier algebra courses. In 2.2, we found we can factor polynomials by performing division as long as we're told some of the factors. And here we have an example from 2.1, and we were able to see a fully factored polynomial. We start off with a polynomial, and then we were able to break it down into what are called linear factors. We see that each one of the values in parentheses has x to the first power, and that lets us know the zero. It's usually the opposite sign. So I have x minus 1 gives me x equals 2, and x plus 2 gives me x minus 1. And the multiplicity, that refers to our exponent. So I have a 2, this is the exponent of 2. This other zero only happens once, thus the multiplicity of 1. Therefore, counting the multiplicities, p of x has 3 zeros. Moving forward. Considering these two examples, we notice that the degree of the function is the same as the number of zeros, counting multiplicities, and this is no coincidence. In general, any polynomial function with degree n greater than 1 will have exactly n zeros provided each zero is counted using its multiplicity. Meaning, however many zeros we have, x equals a number, whatever number that may be, it's also the degree of our polynomial. If we consider the process we use to factor using synthetic division, this should not come as a surprise. Consider any polynomial with degree n. Each time we find a remainder of 0, we're able to factor the polynomial into a linear factor of degree 1, and the second factor that is of degree 1 less the polynomial being divided. If we're able to continue this process until there are only linear factors, meaning to degree 1, so x and your 0, there will be n linear factors that result in n zeros counting multiplicities. With the knowledge of how many zeros counting multiplicities that a given polynomial must have, we now continue with the topic of factoring polynomial functions by division. The slight change from last section will be that none of the factors will be given in the question. To introduce the added dimension of our factoring process, we're going to consider a polynomial function side by side in its factored and unfactored form. So let's consider this factored polynomial, right? Well, we can multiply the first factors. The first factors, and we get an expanded form. And if we multiply our other one in as well, we'll get this long answer. And combine the like terms we get here. So what can we do to get from this step to a more easier way to find the zeros, meaning that way? The above process of multiplication shows that f of x equals 12x cubed minus 8x squared minus 29x plus 17 is the same as this function in this other form. But to find the zeros, which is what we're looking for, we just set each one of these factors separately equal to 0, which we have here. And we can easily find our answer. We get that x is 1/2, x is negative 3 over 2, and x is 5 over 3. And thus we know our zeros. Let's consider separately the numerator and the denominator of the 3 zeros. The three numerators are 1, 3, and 5. Notice that these numbers are factors of 15. So we're talking about numerators, talking about our answers, the numbers on top. So 1, 3, and 5. Which we have here. Notice that these numbers are all factors of 15, the constant of our terminal function, meaning the last number. First, you must look at original multiplication to see that the constant 15 came from the product of all constant terms in the three linear factors. Secondly, you must realize when solving for zeros, the numerator of each zero comes from the constant term in the linear factor. Let me jump to the punchline. What it comes down to is our rational zeros theorem. This says that if f of x, and don't let this notation throw you off, it just means polynomial. If f of x equals a polynomial, is a polynomial function with integer coefficients and leading coefficient not equal to 0 and constant a sub 0, then any rational zero f of x will be in the form p over q, where p is a factor of constant a sub 0 and q is a factor of the leading coefficient. So this notation here just means a polynomial where each a is a coefficient attached to each x. And we have different types of x's. We have x to our highest degree, and then one less, and then it continues until we're left with just an x and then no x. So we're saying here that I can create a fraction. A fraction is going to be made up of p, and p is a factor of the constant a. So this is your p. And then q, the denominator, is a constant, the coefficient of a sub n. So that's q. This fraction will lead to possible zeros. We will use this theorem to create a list of rational numbers that have a chance of being a rational zero for the given function, meaning not all will work, but some may. So when would I want to use rational zeros? I want to use it when there are no ways to factor. This is when we rely on this method. Factoring is the best way to go, if possible. Example 1. Use the rational zeros theorem to create a list of all the rational numbers that may be rational zeros of 3x cubed minus 20x squared plus 23x plus 10. All right, let's label our rule. So our rule says that I have to list my possible zeros, and that's made up from your factors of p divided by your factors of q, where p is your 10 and q is 3. All right, so let's go ahead and list our fraction. So I want factors of 10 divided by factors of 3. All right, so think, how many ways can we get 10? I can get 10 from 1 times 10, 2 times 5, and that's it, right? I can also get 3 from my denominator, 1 times 3, and that's it. So we have listed the factors of 10 and the factors of 3. Let's see how we would like to write them. Any possible rational zero must be in. So we have the same numbers, but we just write them in order. Above, we didn't have them in order. And we want to consider the plus and the minus. Why that plus and the minus? Well, if I'm looking to get 10, how many ways can I get 10? I can get positive 10 from 10 times 1, but when also negative 10 and negative 1 also give you positive 10, and this is just to create positive 10. So therefore, when I'm considering all of my factors, I have to be careful for also the ones that have a negative. So that's where that plus and minus comes from. All right, now I have to think of every combination made. So I can get 1 over 1, which will give me 1, 2 over 1, which will give me 2, 5 over 1 will give me 5, and 10 over 1 will give me 10. All right, so I have some list of factors. I also have to write every number in the numerator by my 3. So 1 over 3 will give me 1/3. 2 over 3 will give me 2/3. 5 over 3 will give me 5/3. And 10 over 3 will give me 10/3. So we have a list here. Notice that plus or minus in the beginning. And I have every one that was divided by that 1. And I also have every number created when I was dividing by that 3. We have them all in one list. Why are we creating this list? Well, this list is going to get us ready for our next step. Let's practice one more time. Try doing this one on your own. Use the rational zeros theorem to create the list of all the rational zeros that may be the rational zeros of g of x. So you want to take your a and your last number, which is your p and your q. Give that a try and you have the answer here. You can pause the video and unpause it when you're ready to continue. Moving forward. Now that we can create a list of possible rational zeros, we factor the polynomials by finding enough numbers in the list that give a remainder of 0. So let's go through example 1 again. Now our question is to completely factor f of x. Well, I can't factor. If I try by grouping, I can group my first 2 and my last 2, and I can't really make anything happen. It doesn't follow our factoring rules for grouping. So this problem is unfactorable. So how can I find all of my linear factors of this polynomial? So I just have x and your number. Well, we can use our rational zeros to make that happen. Moving forward, we just use the rational zeros theorem to create a list of all rational numbers that may be rational zeros. And this is our list. So these are all the probabilities. And if you want to, you can expand this list fully. So I have 1 and -1, right? Plus or minus. I have 2 and -2. I have 5 and -5. I have 10 and -10. I have 1/3 and -1/3. 2/3 and -2/3. 5 over 3 and -5 over 3. 10 over 3 and -10 over 3. And all of these are just our possible rational zeros. It doesn't mean they all work out, but maybe 1 or 2 of them may work. It's not even a guarantee that all 3 of them will come from our rational zeros list. We could have some imaginaries. We have rational zeros, meaning they can be whole numbers or fractions, but no imaginaries, no i's. All right, so how do we go about it? How do we know if something's a zero? Well, I can go through synthetic division. And your goal is to get a 0 at the end. Recall, if we have a 0 at the end, we know it's a factor. And if it's a factor, I have reduced my polynomial by 1 degree. All right, so let's go ahead and do synthetic division. Let's go through our list. So how about 1? If I do synthetic division with 1, and I take my coefficients from my polynomial, I have 3, negative 20, 23, and 10. 3, negative 20, 23, and 10. And I follow my rules of synthetic division. You bring down your first number, and then you multiply and add. Multiply and add, and at the end we got 16. That's our remainder. The remainder is not 0, so x minus 1 is not a factor. Remember, this is the number you have once you get x as your answer. So if you want it in parentheses, it's always a change sign. That's where that x minus 1 comes from. Moving forward. So for my list, I tested negative 1. That one didn't work. Let's move forward and try 1. All right, let's perform synthetic division with 1. I still use my same numbers. I take 3, bring it down, and then your rule is to multiply and add until you're done. My last number is not 0. So therefore, negative 1 is not a factor. Next on my list is 2. We try 2, and with synthetic division, we see that our last number is 0. So because we have 2, we now have factored our polynomial by 1 degree, x minus 2, and my answer is also part of my new factored form. So let's build our answer. Your last number has no x, and then one more x until you're done with your coefficients. So what we did is we have factored. So the function can be factored as this is our synthetic division and this is our answer, which can also be factored as we can factor using our factoring rules to get 3x plus 1 and x minus 5. Let me show you that on the side. So I have 3x squared minus 14, x minus 15. All right, 3 times 15 gives me 75 and 14. So what numbers multiply to give you 75 and add to give you, oh, not 75, 45. 45 and add to give you 15. That's negative 45. Because that's 3 times negative 15. And then you see that what will work to give you negative 14 as a sum. It's a negative. And you proceed factoring that way. If it's a bit unsure to you, you can always check out Module 0 where I have some videos for you. All right, so moving forward, we have it as a list of linear factors. We can do so with any polynomial that we can't begin by factoring. Let's look at example 2. Here I have my list of rational zeros that we created. So I'm taking the factors of 12 and the factors of 2. And we created this list. All right, now I have to test them using synthetic division. And I only want to use synthetic division until either I'm done factoring or I have, for an example, something that can be factored. So we try 1. 1 works. So x minus 1 is an answer. So from here, I get x minus 1. And from here, I get 2x cubed minus 1x squared minus 25x minus 12. So we now have a new factored form, which is here. All right, I have this x minus 3, I'm sorry, 2x cubed. I need to factor that further. Well, I can repeat synthetic division. Even though 1 worked earlier, like we see here, it doesn't mean it can't happen again. It is possible that x minus 1 can be a factor of multiplicity 2 for the original function. So we will continue down the list by checking if 1 is a 0 of our new factored form. 2x cubed minus x squared minus 25x minus 12. Let's try 1 again. If it works, which it can, then 1 repeats. It's a multiplicity of 2. Well, we try 1 again, and we don't get a remainder of 0. So let's go through our list. We try 1, we try -1, no 0. We try 2, no 0. We try -2, and no 0. We try 3, no 0. We try -3, yay, finally a 0. So -3, so this would be x minus -3, which we write it as x plus 3. So x plus 3 is a factor, and we have an answer, which is 2x squared minus 7x minus 4. But remember in the very beginning we had an answer? Don't forget your beginning one, that x minus 1. So now we are here. But now we have a quadratic. So whether it's factorable or not, you can always do quadratic formula. Luckily it is factored. So here is our polynomial as product of linear factors. Let me write that down. As a product of linear factors. Meaning all of my x's are to the first power and product because they're being multiplied. So I have all of my lists of zeros as x minus your 0 listed. Well, as you saw in the problem we just did, it was a lot of effort. I mean, we kind of jumped through it because we have it written down, but if we had to do this by hand, it would take maybe like a good 2-3 minutes per each synthetic division. Not to mention all of the hiccups. I would have totally made some subtraction errors there. But they happen. So is there some guiding light so that we're not just blindly doing synthetic division? And there is. There's Descartes' rule of signs. That S is silent. Descartes' rule of signs. And what that is it gives us an idea of which zeros may work. Make your list of zeros shorter depending on the signs of our polynomial. So let's take a look. When looking back at example 2, we had 16 different numbers in the list of possible rational zeros, and it took 7 different divisions to factor the function down to at most quadratic factors. Descartes' rule of signs will give a way to sometimes shorten the list of rational numbers that may be rational zeros for a given polynomial function. Descartes' rule of signs. Let f of x be a polynomial function with the terms in descending order and real coefficients. 1. The number of positive real zeros is the same as the number of sign changes, or less than the number of any positive integer. 2. The number of negative real zeros is same as the number of sign changes that f negative x, or less than the number of positive even integers. In order to determine the number of sign changes, any polynomial function must be written in descending order, and we must consider the signs from one coefficient to the next. Let's take a look at example 3. Determine the number of sign changes in 5x cubed minus 2x squared minus 3x plus 8. All right, our answer is 2, because from the first sign change, so here we have a positive, and we change from a positive sign to a negative, and then we're cool just with negatives, and then we have another sign changes. So here are our changes. We have a change and a change. We have 2 changes. So because of the first sign change from 5 to -2, and the second change from -3 to -8. 4. Use Descartes' rule of signs to determine the number of possible positive zeros. All right, so let's take a look at our sign changes. I go from positive to negative, that's a sign change. And then negative to positive, that's a sign change. And then positive to negative. The function has terms in descending order. So we simply count the number of sign changes. There are 3 sign changes, which we have highlighted. From 3 to -11, -11 to 9, and 5 to -12. Using Descartes' rule of signs, 3 sign changes for f of x implies that there are 3 or 1 positive real zeros. Determine the number of possible negative zeros. All right, so here we have to do some work. I have to plug in a negative x. And all it's going to do is it might change signs depending on your exponent. So let's take a look. So here I have a negative number raised to an even exponent, so we'll have positive results. A negative raised to an odd exponent will have a negative, and they'll be working with a negative times a negative, making 11 positive. So a negative, and here's a negative, yielding this to be positive. A negative x squared will keep it positive. A negative times a positive, we get minus 5x, and negative 12 stays. So now let's take a look at our sign changes. We see that we start off with a positive and stays positive up until here. That's our first sign change. We only have one sign change. There is only one sign change from 9 to negative 5, so Descartes' rule of signs implies that there is one possible negative zeros. So why is this helpful? Why does Descartes' rule of signs include the phrase or is less than the number of positive even integers? Recall that non-real complex zeros come in pairs, and these numbers are neither positive or negative. We can summarize the results in examples 4 and 5 as below. So, counting the multiplicities of 3x to the fourth power minus 11x cubed plus 9x squared plus 5x minus 12, it has 4 zeros, right? Because our highest degree is 4. In our first case, we saw that there is a possible three positive values, so therefore one has to be negative. And that doesn't mean that none of them are complex. Our case 2, we can have one of them being positive, therefore one being negative, and maybe 2 being complex. If you're not a fan of Descartes' rule of signs, that's okay. You can just do synthetic division until you're done, or until you reach a quadratic. You can just blindly check every number on your list. Descartes just tells you an idea whether you want to test your positives or test any negatives at all, depending on how many possible zeros you might have of those types of signs. If you're to have a problem like this on your exam, I won't ask directly for Descartes' rule of signs, but if I'm asking you to solve a polynomial, I'll give you a hint so you don't spend all your time doing synthetic division. All right, I'll stop the section here. Don't want to make it too long. But you can always post any questions on your discussion on our discussion board or general discussion board, or you can email me or ask your SI. Thank you.